Now it's running.
Yeah.
Okay, folks, this is Bill Adams, just trying to show you a small sample of two important concepts for the HVAC technician to understand before they can really progress on to more complex problems. One of them is series parallel circuits, and the other one is diagnosing the refrigerant cycle. Both very important foundations that must be mastered so that they can be coached into more complex systems later in their career. Starting with down here in this corner, I'm showing a very simple series parallel circuit with a compressor, outdoor fan motor, and a question mark. And that question mark is what I'll explain to you in a second, is what happened to me years ago on a call where the outdoor fan motor was overamping. This is a formula that needs to be understood at some point so that even though voltage is equal to current times resistance, that's on a DC circuit. In an AC circuit, you have what is called impedance. Impedance is a function of frequency from a choke and capacitive uh, conditions of the equipment that you're utilizing. And then the third thing will be the refrigerant cycle itself, where I show very fundamental components that are used in both AC and refrigeration. Uh, Very important issues of how to establish subcooling, superheat, and what those things mean in terms of blockages in the system or what have you, dirty coils, etc., etc. So going back over to the series parallel circuit here, I want to say that on a typical home system like I had a 240 volt system, L1 and L2, and I had the current flow going through the compressor. I don't remember the exact numbers of full load amps. And then there, the outdoor unit was overamping based on its run load rating. Contributing prematurely contributing it to the possibility that the bearing was overheating, causing the problems, I secured a new motor and replaced it in the fan. And you got to be careful. You got to get the capacitor too, because you never ever want to replace a motor without a capacitor, and really don't want to replace a capacitor once you spin the fan and it starts working. You know the capacitor's weak. You can check it with your voltmeter, but you know it's going to be weak. And what is in all likelihood happened, the motor got caused damage to the capacitor. And if you just change the capacitor and not the motor, you'll be returning out there in 2 or 3 months to replace the motor in all likelihood, and the customer's going to be upset unless you put it on the ticket saying that you urge them to allow you to change the motor as well as the capacitor. But this particular problem that came up this day was a situation where I put the outdoor unit in, replaced that right here, and the overamping was still evident. So consequently, what I found upon checking everything, compressor, outdoor unit, every possible amp draw I could think of, I came up with the fact that I located a very weak leak in between the L1 and the L2, between the disconnect and where it went into the unit, the outdoor unit. They had sat there and rubbed the insulation so paper thin that it now was creating an amp draw through the L1 to L2, and that was, of course, changing the current draw through these other two major components, which is the fan motor and the compressor. So this is why a tech has to understand the series parallel circuit and what impacts it in the most bizarre way, because this is not a common problem that you're going to see every day of the week. But it was certainly something that was eradicated once I taped up and secured the insulation so that there's no amp draw at that point forward. And then everything settled down. The compressor dropped down to the full load amps, and the outdoor unit was running under its run load amp rating as well. Explain that to the customer that we got the root cause of what the problem was, and went ahead and left the new motor in because the old motor was most likely irreparably damaged, having ran in that condition for quite some time, because it would heat up and cut off, and then the compressor would run without a condenser fan motor, which is not a good condition at all for anything. It will cause the compressor to fail at some point. It was just luckily the customer had established that the fan wasn't running separate of the compressor when we initially talked, and unfortunately I just didn't know what size motor to bring with me. But anyway, that eradicated this particular problem that particular time, and that is why a student who doesn't know what he doesn't know has to learn series parallel circuits in order to be able to establish these types of issues in the field when nothing fits the norm, because you can't be a parts changer. You want to try and be able to establish what is the root cause of the problem and take it from there. You know, it's just like changing the capacitor, not changing the motor. You got to get that on the ticket, explain to the customer that the capacitor most likely was damaged because the motor was causing a problem, whether it's a bearing failure coming or something along that lines. And to just do the capacitor and not mention anything about the motor would be injustice to your customer, because 2 or 3 months later when it fails, they're going to be mad at you because you didn't tell them about it. And you got to write it on the ticket. That's the key. It makes it easier on your boss to explain why they had to come back out the second time to change the motor, because they weren't allowed to change it the first time. Very important business practices that you need to be respectful of. And once again, Eli the Iceman, you know, voltage leads the current in a choke. Then that's heavily dependent upon frequency. The higher the frequency, the more of a resistance the voltage flow. And this is kind of like one of the principles that Tesla uses in his coil. And then over on this side, capacitor is current leads the voltage in a capacitor, and the higher the frequency, the more the capacitor becomes like a direct short. And these two concepts come together to create surge protectors that you need to put on newer systems, especially because the inverter type compressors they have will have issues of that can be easily damaged by flickering power issues 2 or 3, 4, 5, 6 blocks away or something. That occurs very frequently, unfortunately, today, that will damage a very expensive compressor needlessly if you don't put a surge protector in there. And that's once again a offshoot of the principle of series parallel circuit. That can be covered at a later date in a more involved electrical class, but that's the basic fundamentals that you have to work from, because you know they all follow that principle. Once again, you got to remember is that pressure difference creates current flow. Resistance is like pipe flow in water. Without pressure difference in water, you cannot have flow of water in a pipe system or an elevated water tank or something, a pump, to create that kind of pressure difference. And once you do that, depending on how dirty the pipe is a function of how much water flow you're going to have. Well, the same thing happens with current flow, and this helps you to begin to understand that, because as the pipe resistance becomes greater and greater with time, the water flows less. So too does the current become less if you have a situation where you have a very incomplete electrical circuit somewhere, like under a contactor or something. You cannot draw enough current to make the load perform properly, and as a result you may start pulling excessive current through the other legs. If you have 3-phase power like on a commercial setup, and 2 legs will read very high and one of them will read very low, and eventually that will lead to failure of something to do with the compressor or a condenser fan motor, which will fail the compressor at some point. So you want to address those problems early on, and that's why understanding these concepts enables you to understand the importance of always being attentive to the PMs that you do on rooftops or package units or split systems, because the small things will become big things later on if not addressed properly. So moving on to the refrigeration cycle, which as I mentioned earlier is a very, very important aspect of troubleshooting any system. And here I've drawn a somewhat simple diagram showing the compressor, and then I'm showing the evaporator here on this side after leaving the metering device. I'm kind of reading this backwards, but anyway, in the evaporator, of course, you're picking up heat from the airflow going across the coils and picking that heat up and bringing it back to the compressor, and hopefully not with too much liquid in there. A tiny amount of liquid is essential for refrigerant flow to the motor to cool it, but not enough to destroy the viscosity properties of the oil. If you do that, it'll seize up mechanically, and that's not a good situation. It has to be addressed, because if you got dirty coils up here, you're not picking up enough heat, you'll have too much liquid coming back, and even with the accumulator, which I've drawn in here, that will try to protect the compressor somewhat by holding back the liquid, will eventually be overwhelmed, and the liquid will come on into the compressor and premature failure will take place. But you come out into the condenser over here, and once again you're rejecting the heat that you just picked up from the compressor and the evaporator and getting rid of it outside. This is where your subcooling takes place. And then if you come on around to the liquid receiver, which is usually on refrigeration systems, not necessarily high temperature AC, but you almost always will have a liquid line dryer before the metering device, and then you have the metering device, whether it be a piston, capillary tube, TXV, electronic expansion valve, because that's where the metering takes place of the liquid injecting into a vapor slash liquid form that comes on around into the evaporator, and once again starts picking up heat, which contributes to the superheat going up and up and up in the system, to where when you come back around to the accumulator again, you've got enough superheat, 15 to 20 degrees, maybe, depending on the system. Refrigeration is going to be much lower. It's going to be 4 to 6, 8 to 10, medium, low temperature, depending on which manufacturer. But you've got to know what superheat matches the particular application that you're doing, whether it's walk-in cooler, freezer, whatever. But all these things go together to create parameters: subcooling, superheat, and discharge superheat, which is very important. Carrier Copeland teaches the importance of that to be between 50 and 90 degrees superheat discharge, because that says something's wrong in your system potentially. This is mainly applies to high temperature AC only. When you're talking about refrigeration, low and medium temperature, the rules change somewhat from that aspect, because you don't even rate refrigeration in terms of 12,000 BTUs per ton like you do with high temperature AC. You rate it based upon horsepower. So that's a different rule change for low and medium temperature refrigeration. But once again, you continue on around the circuit and get your subcooling numbers and the metering device, and then continue on to pick up heat again, reject heat in the condenser, pick heat up in the evaporator. Very simple concept. When it comes to heat pump, you really need to speak in terms of outdoor and indoor, because this switches back and forth with the reversing valve. But that's a discussion for a later date. So once again, the basic elements are very, very important here, because if your subcooling is way, way high and your superheat's way, way high, one of the first things you need to begin to think about is what's causing that condition. And typically in that scenario, you can have a blockage in the dryer or the metering device or something to where you cannot pick up heat down here um, in the same way that you did previously with a fully functional dryer or metering device, but you're still picking up heat and you're putting it into the refrigeration, but there's a lot less of it, so the superheat rises and goes up quickly. And then that comes on around into the accumulator, into the compressor, and your discharge superheat is going to go up as well. It's no longer probably going to be between 50 and 90, it may be 100 or more on the discharge superheat. And then you come on around to the condenser where it's trying to reject heat. It's got plenty of time to do that now, so the subcooling numbers go up real high because you can get rid of the heat because you're only moving a small amount of refrigerant and you're stacking it up in the condenser. This is the way you've got to begin to look at the refrigeration cycle as a molecule of a refrigerant molecule traveling around the system and what's happening to you as you progress through these various components. When you do that, you can ascertain in a more solid physical way what's wrong with the cycle itself. Because unlike electrical, which a lot of people want to troubleshoot by changing parts, which is not good. You need to learn hopscotching, which is a topic of another discussion, so that you can ascertain quickly and accurately what's electrically not working right. So too must you learn to ascertain through the various subcooling superheat numbers and discharge superheat to establish what might be the difference between a overcharged system and a dirty coil, because they may have very similar symptoms, but the discharge superheat is going to be way different on one application versus the other. So I can continue along these lines in more detail at a later date, but this is the basic fundamental refrigerant cycle and some of the aspects that you have to begin to master before you finish school and go out into the workplace. Thank you once again, and I look forward to meeting you or discussing, taking any of your calls about any issues that you may not agree with or understand or want more information about. Feel free to contact me at williamdadams@gmail.com or 404-396-0127, and I look forward to hearing back from you as soon as possible, and we'll try and get back to you as quick as possible. Thank you once again. William Adams. Teach Up. Today is 22nd April.